Welcome back. As I mentioned in the previous video, we're going to discuss the four major components of colligative properties. And the first one is vapor pressure. But we haven't actually defined what constitutes a colligative property. In other words, what's the definition of colligative properties? Without going into too much detail, in a nutshell, what colligative properties refers to the actual concentration of solute that you put in a solvent versus the actual nature of the solute itself. In other words, if you have more moles of solute coming from that concentration of the solute, it has a different effect on all four colligative properties than, say, the same substance but you have a lesser concentration or more concentration. So concentration is a key factor in determining how the colligative properties are affected for a given mixture of solute and a solvent. All right, with that said, let's get into vapor pressure. Let's see if we can visualize what are we really referring to as vapor pressure. So say this is a beaker, okay? And you got some water in it, okay? And we're gonna heat it, okay? With a Bunsen burner, okay? Now, as the water molecule, here water is in the liquid phase, okay? As water molecules begins to go into the vapor phase, it becomes, steam, right? This is water in its vapor phase or gas phase or steam, whatever you want to call it. Okay, these molecules, these dots are all water molecules that are in the vapor phase. Now, say each of these will collide with themselves and also with the walls of the container. Okay, they also collide with themselves but also with the walls of the container, leading to a pressure, okay? That's called, let me draw it correctly. This leads to something called vapor pressure, okay? Because as I said, this is a vapor, molecules of water, okay? That pressure in turns, and now say outside this beaker, all of this, we have the atmospheric pressure, which is the room in which the beaker or the lab in which the experiment is conducted. The lab has its own atmospheric pressure, okay? So we're going to call that ATM. PATM means atmospheric pressure. And we're going to call this as P vapor pressure. Okay, when this P atmosphere, which is equals P vapor pressure, the pressure due to the vapor of the water molecule, when it becomes equal to the atmospheric pressure, that's when a liquid boils. Okay, now I've essentially answered some of the components of a boiling point. But keep in mind, vapor pressure is fundamental to boiling point. So it's not something surprising that a liquid boils. Okay, but the idea here is the vapor pressure. Okay, now this is pure solvent, right? What we have in the beaker is just pure water getting heated up, right? But say if you've taken the same beaker, okay, same water molecules, but let's throw in some other color particles, say sodium chloride, which is your table salt, okay? The vapor pressure of the pure solvent, that this component right here, is not the same now because we've added some external agent such as a solute into a solvent. So the vapor pressure is now reduced, okay? So partial vapor pressure is reduced. Okay? That's what we meant by the colligative property definition itself is the solvent pure has a different vapor pressure versus when you add table salt into the beaker containing water, the vapor pressure is not the same. It's usually less, okay? It's usually less, right? Which means it takes actually a little bit longer for the water to boil. Now, given how little salt we add to our, cooking mixtures, it's not going to matter much, but we are going to affect the, the boiling point of water. In fact, if you try to boil a pot containing pure water, I'm saying distilled water, not water containing calcium that we normally get in our taps, and then you take another pot, you put distilled water and you add sodium chloride and boil, you'll see that there is a slight difference in the temperature at which the two boils. The pot containing pure distilled water boils at 100 degrees Celsius, which is the boiling point of water, whereas the pot containing sodium chloride boils at a slightly higher temperature, maybe a couple of degrees. It's not much, but that difference has to be noted, right? And that's because the moment you add the sodium chloride or table salt into a pot of distilled water, the vapor pressure is reduced. How does that influence the liquid leading to higher temperature? Because vapor pressure is reduced, it takes a little bit longer for the liquid to boil, which means it needs more heat, or in other words, it takes, say something boils at 100, because the vapor pressure is reduced, it just takes a little bit longer. In other words, it tends to require more heat than a pure water would, which is why it's called elevation of boiling point. Like I said, I accidentally introduced that. I didn't accidentally. As I'm saying the concept of vapor pressure, I have to draw into boiling point, which is the next concept. Because vapor pressure by itself, it's a fundamental. It's not something that's going to stand alone and make a lot of sense until we actually put it into the context of boiling point, right? Now, there is something that I want you to know in the process, which is a Raos Law, okay, which allows us to make sense of the concept of vapor pressure more mathematically, okay? I know some of you like to see things mathematically than others. Some of you might be more interested in the drawing I have here. Some of you might be more interested in the mathematics to understand the science behind it. And to do that, we're going to write an equation called pressure of the solution, or in other words, we're going to call it the pressure of the solution equals mole fraction of the solute times the pressure of the pure solvent. Now, there are a few things I want you to take note of here. And the first one is the superscript. Whenever you have a component such as pressure, temperature, volume, whatever be it, and you put a superscript, it refers to the pure form of that substance. So whenever we refer to pure solvent, we put a subscript. So this is the mathematical equation that I want you to remember, which is vapor pressure of a solution equals mole fraction of a solute times the vapor pressure of pure solvent. So let me write this new term here. This is nothing but mole fraction of solute. Okay, and P0 solvent is the vapor pressure of the pure solvent. Okay, it's only through this mechanism we can systematically understand how much is the vapor pressure reduced. Okay, we're going to do two different problems where you will see that I'm using the same solute, okay? And then you will see how much the vapor pressure is smaller compared to the vapor pressure of the pure solvent, okay? So this is Raos law, which is pressure of vapor pressure or pressure of a solution equals the mole fraction of the solute times the vapor pressure or pressure of the pure solvent, okay? Now, this is where I want to stop the video because the next two videos, I'm going to work out two separate problems, one for each video, and then I would mathematically show you this phrase right here, that and the example I told you, that how a pot of distilled water versus pot of distilled water plus sodium chloride, the pot with the sodium chloride has a slightly higher boiling point. So it's contradiction to the common misconception that people tell you, add table salt to your water, it'll boil faster. That's actually not true. It cannot boil before 100 degrees Celsius, which is actually the boiling point of water. In fact, the opposite is true. That is, because that vapor pressure is reduced, the water actually boils at slightly more than 100 degrees, in contrary to belief that you may have heard that, oh, add salt to water, your water would boil faster. That is not true. That is complete contradiction to what science suggests. And we're going to see that misconception being refuted in the two mathematical problems we're going to do. And then you don't need to memorize the Raos law. It will be on the back of the appendix on a test, or for homework and quizzes, you already have it. So I'm going to rewrite the law for each of the two problems that I'm going to work out, and then you will see it for yourself that the vapor pressure is reduced in a solution compared to a solvent. All right, so stay tuned.